In this video, we'll show how to calibrate time-specific ecological niche models using temr package. Time-specific ecological niche models are calibrated with time-specific and high-resolution environmental data that encompass a longer period than the one that is considered in traditional niche modeling. The image refers to a part of the traditional modeling process. We observe the spatial and environmental distribution of a set of occurrences with different temporality. Traditional modeling employs environmental layers that cover a short period and usually represent the average environmental data from different years. In this example, we have 14 occurrences, from which 10 would be dismissed because they fall outside the period covered by the available environmental data. As we can see, we've lost a significant amount of information. Time-specific niche modeling is a novel approach that allows calibrating niche models with high temporal resolution spatial information, which aims to reduce niche estimation biases. Although time-specific ecological models could improve distribution estimates, few works have used them. The goal of temr package is to provide methods and functions to calibrate time-specific niche models, letting users execute a strict calibration and selection process of niche models based on ellipsoids, as well as functions to project the potential distribution in the present and in global change scenarios. The image refers to the time-specific modeling. Time-specific ecological niche models allows us to use environmental layers with a temporal resolution that encompasses a longer period. As we can see, we have the same set of occurrences. Through time-specific niche modeling, we can retrieve the environmental information of the 14 occurrences, since the environmental layers we use cover a longer period and also have a temporal resolution. In other words, we have specific environmental data for the different years within the period. For example, for these two occurrences in the same pixel, we could get different environmental data for different years, since we have layers for 1910 and layers for 2014. In time-specific modeling, we can include a greater number of occurrences, which allows us to recover a greater amount of information and make a better estimation of the ecological niche. The goal of temr package is to provide methods and functions to calibrate time-specific niche models, letting users execute a strict calibration and selection process of niche models based on ellipsoids, as well as functions to project the potential distribution in the present and in global change scenarios. In this tutorial, we'll illustrate the process of time-specific model calibration. Before starting, we'd like to say that all the data that will be used in this example is already included in the package. The first step is to call the package. If we haven't installed it, we can use these lines to do it. The next step is to load the occurrence data. This data belongs to the species Abronia gramínea. The occurrences have a temporality between 1939 and 2016. Abronia gramínea is a lizard with a limited geographical distribution and is endemic to Veracruz and Puebla. We load the data and we can see how it is structured. Once we have our occurrence data, we'll specify the path of the directory where the time-specific environmental layers are stored. We see the path and we'll run the next line to explore the directories that are contained within the path. As we can see, the path stores other directories named with the years of the environmental layers. With the following lines, we explore the TIFF format files within two of these directories. As we can see, in the directory of each year, there are the same environmental layers. In the next step, we'll use the sp temporal data function to create an object named sp temporal modeling. This object will allow us to work with time-specific data. To parameterize this function, we need to specify the object that contains the occurrences data, as well as the names of the columns that contain the coordinates information. The sp datebar argument asks us to indicate the column that has the date of each occurrence. The octdate format and layers date format argument asks us to indicate the date format of the occurrence data and the environmental layers. In this case, we are using y, which corresponds to year. The layers by date dir argument asks us to indicate the directory in which the layers are stored. And finally, layers x asks us to indicate the format of our layers. We run the function. The resulting object, named ABT, has 4 elements. We'll explore the element called temporal DF, which contains the following data. The first two columns corresponds to the longitude and latitude coordinates. The third and fourth column contains the temporality of each of the occurrences, and the fifth column contains the path in which the environmental layers from each year are stored. Next, we'll clean spatial duplicates with the cleanedUp_by_date function. This function cleans the data considering the time variable and a distance threshold. Before running the function, we'll see how many occurrences we have initially. We run the function, and we can see how many occurrences we have after the thinning. The cleanedUp_by_date function allows us to clean duplicates per pixel using a raster mask. This will be the raster layer that we'll use. We can see how it looks in geographical space, and we run the function. As we can see, this method recovers a greater number of occurrences. As an exercise, we'll test how many occurrences we would obtain through the additional duplicate cleaning. We'll use the cleanedUp function and a raster mask to dismiss spatial duplicates per pixel. We run the function. As we can see, when we include the temporal variable in duplicate cleaning, we can recover a greater number of occurrences, since some points may be spatially duplicated, but if they belong to different dates, they are not considered as duplicates. The next step is to extract the environmental data from the occurrences. We'll use the x_by_date function that extracts the environmental information by year. This function also generates the datasets for train and test, using a random partition with a defined proportion. In this function, the argument thisSpecies asks us to indicate the SP temporal modeling object with which we are working. In the argument trainProp, we'll indicate the proportion for the train data. Before executing the function, we'll run this line to run the process in parallel. We run the function and wait. We'll explore the temporal DF element and see that we already have the time-specific environmental data for each occurrence. We also have a column that indicates whether the point was assigned to the train or test dataset. Next, we'll generate an environmental background. This is necessary for the temp package to run the rock and partial rock test and estimate the prevalence of the species. To generate environmental backgrounds, 10,000 points will be randomly taken using as a calibration area a neighborhood of 10 pixels around each occurrence. To parameterize the function, we'll use the object resulting from the x_by_date function. As we know, this object contains the environmental information of the occurrences. The buffer NGBS argument asks us to indicate the number of neighboring pixels to generate the calibration area. And finally, the MVG argument asks us to indicate the number of points that will be generated. We run the function and wait. Before continuing with the calibration process, we would like to introduce the function TDF to SWD, which is an abbreviation of temporal data frame to samples with data. The temp package uses minimum volume ellipsoids to create niche models. However, we know that other algorithms exist, which is why the temp package includes a function that allows exporting the time-specific data to SWD format. This format can be used in other algorithms, such as maxent. With the following line, we'll convert our SP temporal modeling object to samples with data format. We run the function and see the samples with data format. We can also export the environmental background to SWD. The next step in the modeling process is to select the environmental variables that will be used to calibrate the model. We'll use the correlation finder function. This function filters variables according to a correlation threshold, which is important to avoid problems related to collinearity. In this function, the environmental data argument asks us to indicate the variables to be analyzed. The method argument asks us to indicate the method that will be used to estimate the correlation matrix. And finally, the threshold argument is the threshold that we'll use to determine that the correlation is high. We run the function, and with the following lines, we'll observe the selected variables. At this point, we have the necessary for the calibration. We have the clean occurrences, the environmental data, the background data, and the selected environmental variables. It is time to use the temp selection function to calibrate the time-specific ecological niche models. This function uses the background object. The OM criteria argument asks us to specify the omission rate criteria to select the models. Ellipsoid level is the proportion of points to be included in the ellipsoid model. Bars to fit asks us to indicate the name of the selected variables, and bars to fit requires a numerical vector indicating the number of dimensions used to build ellipsoid models. Proc is whether or not we want to perform the partial ROC test. Random percent refers to the random percentage of data that will be used to start the partial ROC test. The number of iteration argument asks us to indicate the number of iterations of the partial ROC test. The parallel argument asks us to specify whether or not the calibration process will be executed in parallel. And finally, n cores is the number of cores used in the parallel process. We run the function and wait. As we can see, a total of 492 models were generated, and only 27 passed the selection criteria. The mode cell object has 5 elements. We'll explore the modes table element, which contains the results of the selection process. The table contains detailed information about the models. We can see the variables of each model, the omission rate for the training and test data, the IDs of the occurrences that were not predicted, the prevalence of the background, etc. Once we have the results of the selection process, we can project models using the predict method. We'll project a model using the environmental layers for the year 2016. With this line, we load the layers and run the function. We can observe the ellipsoid model in a three-dimensional space. As an exercise, we'll also project the model using the environmental layers for the period 1970 to 2000. We load the layers and run the function. Here's the ellipsoid model in a three-dimensional space. Now we'll project the model in geographic space. We run the following lines and observe the projection of the model using environmental information from the year 2016 and also for the period from 1970 to 2000. Here we can see both predictions. As a final exercise, we'll show the differences between a traditional ecological niche model and a time-specific ecological niche model. For the traditional model, we'll use environmental layers for the period between 1970 and 2000, and we'll use the dataset resulting from the cleaning of spatial duplicates with the traditional method. We load the layers and extract the environmental information of the occurrence data from the AB1 dataset. Now we'll project both models. The pink ellipsoid represents the time-specific niche model. The green one represents an ellipsoid model fitted using the traditional approach. Note that both ellipsoids differ in size and shape. In traditional approach, we can see a subestimation of the environmental values where the intrinsic growth rate might be positive. With this exercise, we finish this tutorial, hoping that it has been useful to you.